Okay, so let me continue. So we have seen the following. We get this kind of estimate. We used the following. C1, say, which is this called the Poincare inequality. There are a class of this kind of inequalities. So then our job is to understand what this equation. That's the second question. And the answer is a weak solution. Namely that, let me put a minus sign to make the algebra a little bit prettier. Is I multiply the equation by V, integrate. Then I define this identity as my understanding of the PDE. It's really, it takes human being like 30 years to understand this step. Nowadays, everybody think this is easy. Then to prove the existence is really, really easy to do. So what you do is you just define this as an inner product. This is abstract. You take this as a definition. Then all the functions with weak derivative in L2 form a Hilbert space under this new defined dot product. You define all these functions H1. Of course, the understanding that takes a while to define, but suppose you can do it, then this is a perfect Hilbert space. Then this is a norm, rather than square root of it, size of all the things. So then, in order to prove there's a solution satisfies this identity for all V become triviality. So this is a inner product. And if you want to show there's U such that this is true for all V, you only have to show that this is a continuously bounded linear functional, which is trivial. You did it already, actually. So by Rees representation theorem, which says that any continuous linear functional can be represented by the dot product. So you only have to do that, and which is trivial. How do you prove this is bounded by this norm? Is actually what we did already. This is V squared. And this is less or equals to, by this Poincare inequality, greater than V squared. And this is the norm. the corresponding norm. Right? That's the norm, and that is a, say, let me define that. So what's that mean? This is, if you're thinking V as a variable, this is clearly linear in V and bounded. So by representation theorem, there's a U such that this holds. Then that's a weak solution comes almost by free. So then what's our next job? Our job is to back to the classical theory. Is that this is the understanding of this in this sense. Then how do we understand they are really equal? So for example, if this holds in the weak sense, can you find one point left equals right? It's not easy to do. You know, it's like it's identity in the weak sense, and it's even more difficult is suppose f is really classical. Say x is x1 squared, right? Then can you show like f would be smooth? Then can you show like u is really have a classical second order derivative, and they are equal? All those kind of questions is called regularity theory. So regularity theory can be thought as, suppose there's a way you can find a solution in reasonable fashion. And the reasonable fashion usually from a very easy estimate, say maximum principle. Here is this H1 estimate. So next you want to show that it really satisfies the reasonable estimate as expected. And that's the regularity theory. So let me go back to the easiest regularity theory. Is suppose, say, U is square. This is, say, bounded. And this square is bounded. How does this U really behave better than L2? And to understand that, and I won't give you a proof. I just try to show you a reasonable understanding, and I hope you agree, and that helps everybody to remember the soberative embedding. So before I do that, the C alpha space is crucial for understanding all these kind of businesses. I will show you in my next lecture. C alpha space comes very naturally for a scaling invariant classes. But before I talk about, let me throw the space to you right away. So C alpha space is the following. It's all those functions. It has a fixed modulus of continuity. Soup. Let me always think about the in ball one. All these functions such that when this x, y gets close enough, this ratio always bounded. And a geometrical picture is the following. So here is a ball one. It's just like a ellipsis function. It's instead of alpha equals 1, what you draw is like at every point you draw this like beautiful lily flower, and it grows like you backyard garden. If you can draw that, it says U is holder continuous by this exponential alpha, and this notation is C alpha ball 1. And this kind of once you multiple continuity is fixed, you can always put a bar here. It's like bar are not bar; they are really equivalent. It's a holder continuity can be always extended to this boundary. But in terms of geometry, how this alpha behaves, if U is ellipsis, which is defined like C1 here, which is really bad notation, but we use that all the time. So is you look at this quantity, L infinity ball 1 is more or less like R times U's ellipsis norm. Right? This is the definition. So not quite. It's like less or equals to. That's the, of course. So this, how this function closely approximate by the reasonable number, this speed power measures how this how this function regularity, and for this C alpha, you will see this kind of properties. Actually, less or equal R to the R alpha, that number, and I define this number by a semi-norm C alpha, and you can see this is clearly true. So this more or less, this you see this how this number vanishes with respect to R measures this alpha regularity. Then I want you to go a little bit beyond what you can see from this line. You follow this, for example, U is in L2. Then I want you to observe what is Schauder regularity of U is L2, or how this thing decays with respect to R. And clearly U is this number, I cannot write it down. So forget that part. Let me try to compute this. Right? Very, very naive. I just want to say, this was very successful. So let me go back a little bit. We all agreed the physical correct observation is 1. We unified everything. So if you unify the understanding of how this approximates by a constant is by pull up the coordinate, look at how this decays. We observe this beautifully. This is equivalent to this fact. U of x minus U of 0 divided by x to the alpha less or equal to this number. Say that's 1, less or equals 1. Then this and this fact, they are the same, right? Now, we do it on L2. Why not? Then what do you observe? This is, of course, you go back to the native coordinate. This x is the unified coordinate. This variable is the native variable, like here you use Portuguese, right? So if you name this is your x, then this is this x over r, and if you pull it outside, is there. Then of course this if x runs ball 1, then the r times x runs over ball r. Exactly like that. So then, what can you say? This exactly equals to 1 over r to the n over 2, or rather r to the minus n over 2, integral ball r u squared dx, square root, right? Then this less or equals to, people warn me I shouldn't do this, but up to a constant r to the minus n over 2. Then by your naked eye, you discover that U is, if I borrow the language, is that satisfy this condition, U is C alpha. Then you discover that U is minus n over 2, Schauder continuity. And that you should think about. So L2 is C minus n over 2 regular. It's negative, but that should be the correct way of thinking. And And you do the same thing. LP is C minus N over P regular. I won't do the computation, but if gradient U is in L2, then you do the same computation. Exactly, very, very easy. Elementary, you pull out the coordinates, see how it behaves, how it's away from a constant. Then you discover that U is C1 minus N over 2. And put everything. I mean, this is really complicated. You try to forget everything. Then let me show you one sentence. Is that WKP is K minus Pn regular. That's the only thing you have to remember. And another sentence is that embedding theorem usually leaves, I mean, it's always actually leaves this index invariant. Then you forget everything else. Let me give you a couple of examples. Then we move on. So W12 is the same thing as let me write down W1P. Is U is the function. U is in L2 LP. Gradient U is in LP. And his Schauder continuity is 1 minus P over N. This number can be positive, can be negative. No problem. Then if this number is positive, it means that W1P, once this is positive, you lose the randomness. You see a classical picture. You can draw those lily flowers. You do. Then this embeds to C1 minus N over P. And this number always be, if bigger than 0, it's guaranteed to be less than 1. Right? But once this number is negative, of course, you don't see a physical regularity. The regularity is in the distribution function. Then what should you write? You write LQ space, right? So W1P embed to LQ. And I promise you this Q is invariant by that counting. And this Schauder continuity is this number. And this Schauder continuity is 0 minus N over Q. And you want them equal. That's exactly the number you should remember. And there's nothing to remember. Okay, and also, also if you compute the trace theorem, it also leaves the index invariant. U is in W, say 1P of ball 1. You want to understand what's going on. You restrict to the boundary. This will be in W, some crescent space of P of ball 1, right? The only thing you want to find that. And what's that number? Then that number should leave everything invariant. Then you put this together, then you get everything. So this question mark minus P. But the boundary of this thing is n minus 1 dimensional. Equals to 1 minus Pn. Right? They are the same. And you get a question mark. This and that cancels. So this equals to 1 minus 1 over P, right? The minus is this. So you restrict to the boundary is in W 1 minus P. That's the. If you want, you can go smaller dimension. It's like this. if the situation arises. The only thing you have to be careful is when this index is integer, you have to be careful. And this regularity, you are not allowed to go up. It's always the LPness always getting bigger, the smoothness getting less is the direction you want to go. But later on, at the end of the day, today I will show you that for Holder space, there are so many equivalent norms, and in many point of view, they are all equivalent. But this is like a warm up. If you have a control of the derivative in all directions, the regularity theory is actually soberly embedding. And the PDE is you only have control of Laplacian of one linear combination of second order derivative. Then you want to get the control of U in proper fashion. Okay, so now go back to this. We more or less proved this. If you do that computation, we prove this. We have actually this can be h -1. Is if you do be a little bit liberal, you can solve this kind of equations. You have existence and uniqueness of weak solutions. So what you observed is what existence really means is this U is defined inside, and the information of U is coming from everywhere. In the case f equals to 0, the U's value would be a negotiation of result from the boundary. And the result of the negotiation is U is regular. All the derivative U is bounded. In the case, U is smooth. I prove it. All the derivative is bounded. 2 is you look at f. If f is like really bad, Laplacian U will be equally bad, right? Because its sum equals f. But if you look at U here, what say defines Hessian of U? It's really complicated. If f here changes a little bit, this d squared U, because it's globally defined, will have an influence of this Hessian from near and far. So that's basically the situation. So there is a saying that where is the like a high frequency, a low frequency? The boundary data phi from U is kind of lower frequency. No matter how bad phi is, the influence to the interior is always smoothing out. That's the regularity of harmonics function part. Then this f part is like a local thing. It's how good f is dictates exactly how U behaves, because that's the pure algebraic identity. But nevertheless, what I want to prove is the following amazing theorem. If I write it down, it's almost beyond belief. It's following theorem. It's called Schauder. Is the following: just f Laplacian U equals to f of x. I assume, say, f is C alpha in ball 1. So what that means is f has a fixed module of continuity. So when 2 points close, this f is the area is like a distant to a power, nothing more, nothing less. What the PD says, you have one linear combination of second order derivative behave that way. Then the conclusion is that then the Hessian is in C alpha ball 1. This is alpha. simply impossible. I mean, how could something like that be true? Right? What it says that a linear combination second-order derivative is geometrically related with the distances to a power. Then the conclusion is that all the second-order derivatives behave basically the same way. Of course, you have to say it in a reasonable fashion, because this I kind of cheat a little bit. This is with estimate is the Hessian C alpha half is universal constant. I abuse this C0 a lot. This is F C alpha normal 1. I mean, I have to be everything like a reasonable, say. I add that, otherwise I can be crazy, then use area infinity. But the pure fact of the statement is really beyond, almost beyond reason. How could it be true? And this is, you can see once I write it down, it is fundamental. It makes our life a lot easier. Not only that, this has other profound applications because the following is a theorem plan. Say Laplacian U equals to F. Between, I mean, it's like over bar. This pair. This is like the linear algebra of PDE. Once you see this operator carried with the boundary condition is isomorphism, then you can solve nonlinear PDEs. Whenever f is C to alpha up to the boundary. Not only you can show locally, you can do all the way up to the boundary. Actually, this space, this couple, and this Laplacian, they are isomorphisms. So that's how fundamental it is. Is one operator controls n square of them. And this kind of thing, since it's so nice, it can be perturbed because this f can be thought as zeros perturbation. Then Laplacian is you can perturb that too. Then I won't state it, but you can do a lot from this. So how do you prove it? And I have like 42 minutes. I can give you a couple of proofs. The first proof I want to say that this area infinity approach is also really the proof is how do you understand higher order derivatives by the things you can easily observe. What I mean is, let me restate the lemmas in a way that is useful for my proof. So Laplacian U equals to F in ball 1. U equals to 0 on ball 1 on the boundary. Then U of X is less or equals 1 over. I even remember this kind of. It's so easy. I remember every detail. So the proof is really, really easy to do. I better put a minus sign. You understand this F as a heating source. You want to heat up the material of U, and suppose U is you annihilate the influence from the boundary. You put it 0. You want to understand how F influence to U. And you want to see that suppose, I mean this, you want to prove this, of course you can assume that equals 1. right? You want to look at all the heat source to heat it up so that the heat source is less or equals to 1. Then how much the maximum heat you can make, of course, the maximum one is you make the heat source under this kind of situation the biggest possible. The biggest possible would be the capital U would be exactly 1, right? Then every solution is, by the maximum principle, is less or equals to this capital U, because Laplacian little u is less or equals to Laplacian capital U with minus sign, because this is 1 is the biggest among all those norms less or equals to 1, right? So by maximum principle, U is less or equals to capital U. Clear? But this U is really symmetric. If you want, you can write it down. And you can make a guess. It's 1 minus x squared over 2n. And that's the proof. And of course, as you can turn the picture other way around. It's less or equals to that. So that estimate the influence of f directly to the L infinity norm of u. And the immediate consequence is, let me write it here. Corollary would be Laplacian u equals f. U equals 0. Boundary. It's every single line is like a cakewalk. But this, in terms of regularity theory, this is like a junk. Because this, I assume f is bounded, right? I get the u's L infinity norm is bounded. But here, what I'm saying that if f is Holder continuous, is the whole Hessian is in the same space. It's the same space. Here's rather bad. Is L infinity to use L infinity. I lose 2 derivatives. But nevertheless, I can discover my truth from this junk estimate. Here's a key lemma. Is the following: is that for any this is a little bit long. I will explain the geometry. This is fixed. So then there exists a R0 epsilon 0. They are all fixed. Depends only on alpha under the dimension, such that if Laplacian u equals to f with plus or minus and doesn't matter really in part 1, and the u L infinity is less or equals 1 in part 1. Suppose that with f's L infinity part 1 less or equals to epsilon 0. Suppose that then there exists a second order harmonic polynomial P. So I can write it down if I want. I abuse a C very, very badly, such that u minus P L infinity for R0 is less or equals R0 2 plus alpha. This is a little bit long, but let me draw the picture, then try to convince you that once I have that lemma, we are done. And that lemma is like one-line proof. Let me first explain the geometry. What does that mean? So a couple of pictures. So what's that mean? L is this. This means, let me again draw this U. This is my X. All the U's, so less or equals 1, basically like a black box. This is the range you could be freely go. U is from -1 to 1. It's like all the all those things. But you assume U is a graph, of course, but it's jumping up and down. Then I assume that a PDE. And also, what does this mean? This is, say, almost like a 0, right? So then what the limiting case of this statement is that if f is equal to 0, then U is harmonic, right? If U is a harmonic, and U is bounded by 1, of course, locally, U will be smooth. So U minus a polynomial, I can say as regular as I want. So this is quite believable. This is U minus P actually is a third order vanishing because U will be smooth. But with a tiny perturbation, I make that possible. It's quite believable. And what is thing is what is the result of this picture? I add a PDE. Then I can find the universal scale R0. I can find a very nice second order polynomial. And use error in this scale R0 is very, very tiny. And the gap here is R0, 2 plus alpha. The geometry will be U will behave something like that. Near the boundary is wobbles. Then inside here, it's in a very tiny strip. And the strip, the ratio, the mathematics, the most important is the ratio. The height divided by base is something like that. So in the general understanding of Sobolev space, it's really R0 plus 2 plus alpha regularity already, but only in this scale. But once you can do this, you are done. Because what it says is that under the physical, under favorite situations, the black box in the middle, you can squeeze all the way, like a super powerful squeeze it to this power. Then, of course, this thing and this black box to mathematicians, they are the same. And topologically, we assume a lot of things like a ball. But this is a box to me. I will do the computation. How do you make that into a box? If you think this as a box, then in this scale, if the situation is also to your favorite, then of course you can squeeze it again, right? Then you iterate this thing. Then what do you observe at the origin? Is every step you squeeze it by this R0 to the 2 plus alpha scale. Then at the end, you get very close approximation. The approximation is so precise, you get a second order derivative precise. Not only that, the error will be exactly R0 to the 2 plus alpha. And that's the proof. OK, so there are a lot of physical and philosophical discussion I have to make, but that's basically the proof. And let me go over it, then make the discussions. So proof. So f is almost like a zero. So you get his behavior from two parts. One is f, one is the boundary. So its boundary is smooth part. So you isolated that first. Then the difference will be very much under controlled. Right? Then my lemma tell me that u of x minus, I mean this is pointwise, less or equal 1 over 2n epsilon 0. Right? Then this is once this is so small, you don't even have to think about it, what's going on here. Then this h is a L infinity for 1 will be less or equal to 1 by the Maxim principle. because the boundary is less or equals 1. So when you extend it harmonically inside, it's also bounded by 1. So this implies any order of derivative, particularly his third order derivative, about half, say, would be bounded by, say, C1 is the universal constant. So now, of course, you separate H into two parts. One is his second order polynomial part. This is second order Taylor polynomial. And this is actually harmonic. Did I say? Yeah. So because the Taylor polynomial of harmonic function, clearly harmonic, will be less or equal to epsilon 0 to n. And the error of this from that will be a constant divided by x to the cube times a number like that. Then you see that the error is so small. This is arbitrarily small. That's a cubic order. So of course, this is less or equals to, you first look at that because this is free. You don't even think about it. So that is less or equals to, say, R0 2 plus alpha O over 2. This is if R0 is sufficiently small and fixed. That's the moment you fix it forever. And this R0 is really a physical constant, independent of you. This is the statement very, very careful. Like before you appears, R0 appeared. Then you take epsilon 0 over 2. This is the first step. This is the second step. If this is less, it's say exactly equal to that number, then you double it up. That's exactly what you want to prove. Okay, so philosophically is that the hard part of this derivative estimate and the second order derivative estimate is to find what is the second order derivative really is, particularly say for nonlinear equation, for Monge-Albert equation for minimum surface. It's quite nonlinear, depends on you everywhere. So what does this does? This is like a nonlinear argument. By the way, this is argumented in Louis' paper. You first find a reasonable approximation. This is a not use second order derivative at the origin yet, but this is the most reasonable educated guess of the second order derivative u, and the error is under control. Then once you get this very nice approximation, so this step like 99% correct, you have 1% error. But mathematically 1% error still an error. It's not second order derivative. So you want to get a second order derivative. You want to get the second order derivatives exactly what's that value. But that is okay because once you get 99% correct with 1% error, every step you threw away 99% of the errors. Then you do it infinitely many times. What do you got? You get precise identity. And in order to get second order derivative, you have to get what it exactly is. And this is the way to get it. You don't get it precisely at the beginning, but through infinitely many steps, you get it. So by one sentence is that error divided by infinity equals to 0. Okay, that's the philosophy behind it. Really, we do infinitely many steps. And one thing I didn't say is that how the piece derivative bound depends on you. That is actually because this picture converts so fast. It's automatic. So necessarily, like A plus B plus C is less or equals to a universal constant. There are many ways to see it. For example, R0, right, is is universal. So I know U is less or equals 1, right? And the error is almost like a 0, say less or equals 1. So P's error infinity would be less or equals 1 in that little ball. So his second order derivative would be universally bounded. So this is totally free, and that is the proof. Okay, to convince you further, let me do the iteration. Really show you that you can really capture exactly what the second order derivative is. Okay, so iteration. And all the regularity theory is in this nature, particularly for nonlinear things. You make a guess, then you iterate. At the very end, you get a precise thing. So iteration is that at every step, you don't think about the conditions. You put the conditions later on. You assume this in ball 1. As a condition, I will add it more. U is let me do this. I assume F is small somehow. We'll provide it later. And then they are harmonic polynomials. Pk of x with half x transpose akx plus such that u minus pk L infinity ball R0 k is less or equals R0 2k alpha k. And with all the estimates you want. I abuse that really badly, but this second order derivative converge in the alpha fashion. Then the first order derivative is C1 plus alpha fashion. Then the constant term is even with faster speed. Then you can see that they converge. And since the error is a geometrical series, then what do we want? You want me to prove this first, then talk about consequences. Let me prove it first. And I also have to write that down. So you take a P0 of the polynomial identically 0, of course, right? It's like, because this is like a for all case, right? Then P1 of x as in the key lemma, as in the lemma. And in that lemma is a k equals to 0, right? K equals 0. A1 plus minus 0 is less than C0 to the 0th power. So really everything as I promised. And I need a condition that L infinity ball are 0 less or equals to epsilon 0 now. That's the first condition. I will provide it whatever I need there. Then assume it's true for k. Namely, I have this kind of estimate with all that. I better switch the index, k minus 1, because otherwise, right? Otherwise, it's like for all k, they are fine, but inductively, I better write that way. Suppose it's true for k, then namely you have this inequality. Then what do? This is a very thin box. deformed by the polynomial. Then I want to make it a unit size with vertical size 1. And the way to do it is pretty easy. It's this inequality right in front of you. You normalize it. This is to make this horizontal dimension into 1. And this minus is to make the bottom polynomial, to make this line flat. You know, this is a deformed box. How can you make like this box? Use a minus polynomial, it's become flat. Then you normalize whatever there is. It's become 1. Right? And what's the equation? When you apply this, it's gone. So this equals to f. When you take a Laplacian, you get square. And you have to divide this. When you do this, you just write down whatever you got, no question asked. The iteration need anything. What do you say? You say, yes, sir. Just carry on. Okay? You don't think about it. So then what is the condition? The condition is R0 2k f R0 k x. This number L infinity norm, this all equals to our predetermined epsilon 0. Because if that's satisfied, you have next step. Then it implies that this u minus pk R0 kx divided by R0 2 plus alpha minus, you find a polynomial. This all equals to R0 2 plus alpha in ball R0, right? You just write it down. Then you have to assume this is the condition. Just move to the theorem. And don't think about it. Okay? And you think about it at the very end. Then you look at what is this. You change your variable back. You multiply this to there. When this map with that, this part, the correction, becomes very, very tiny. It's like really beyond the naked eye can see almost. And the error is as claimed. Right? This is the next step. Then of course, this is your x. Then this thing. Let me forget this variable. This variable is important, by the way. Then do this plus sign, right? Then this is you define this like pk plus 1 of x. That's it. Then what's the error? I claim that the coefficient decays in the correct fashion. Then it's exactly as it is. I haven't really scaled back the coordinate yet. So this is still in ball R. Then you write this estimate in the native variable. So namely, you name this your x. If you call this your x, this is R0. Oh, let me write down one more formula because it's you get u of x. Everything is native now. It's pk of x plus R0 2 plus alpha k. P, this is unit 1 polynomial. Less or equals R0 1 plus k 2 2 plus alpha. Every single step is crystal clear. Okay, very, very easy. So now, of course, you define this your pkx, because everything is stated in the native variable. This is unified, normalized variable. They are different. Pardon me, this is this plus 1. Then what's the coefficient's error? It's here, right? This pk from the coefficient is exactly here. Then let's observe what is the estimate of each of the derivatives. What happened to the second order derivative? Second order derivative is x squared over rk squared, right? So rk squared cancels with k squared. So the error is r0 alpha to the k, exactly as I promised. It's r0 to the k times c0. C0, again, is universal. Then the first order derivative is x over r0k times that. So you see the error is 1 plus alpha to the k. The constant term, this change of variable has nothing to do with it. So constant term is a constant times a bounded constant times that. So each coefficient depends on each u. U is a physical observation. Then C0 is a physical law. That's universal. So it's like the error is estimated uniformly, and each coefficient decays according to your favor. So then what you got? You got this error estimate. If this holds, right? So this less or equals r0 2 plus alpha to the k involve r0 to the k. And since the coefficient has those kind of faster decay, it's very easy to prove there's a limit because they converge, right? This less or this equals to c, maybe c1 say r0 k 2 plus alpha. The error is exactly as the leading term because it's a geometrical involve r0k. Now, another important idea, not important because if you believe my picture, all this algebra, it has to be true. So now, what is a variable? You better think like this is your variable, right? This is k equals to 0, 1, 2, 3. This is the variable. So if you call this your x, you see, those two are interchangeable. Not only that, is you can literally interchangeable is x comparable with uk for x in ball r0k minus ball r0k plus 1. In this ring, all the axis is like that, right? So now then this is in that ring is c1 maybe tilde x to 2 plus alpha. You see the error, everything fall into places, and this can be also said exactly like that. And you introduce, you put this error into that. Everything is this variable to x to the 2 plus alpha power. So at the very end, you get u of x minus p of infinity of x less or equals to x to the 2 plus alpha c1 tilde in each of the ring. But union of the ring is the whole ball. So it's true everywhere. So this is. So I prove this estimates holds for every single x in the whole ball. Under the condition, this is true for every k. Okay, this is a condition, but that's it. So now I have to understand what is that condition. So what is that condition? Using the same interchange variable with R0 to the k, that condition is nothing but, it's very, very close to C0 x to the alpha. Really, they are literally the same. And what this says, this is equivalent to say f0 has to be 0. And this number, if you like, you better define this like a pointwise Holder norm. If you may. It really deserves a name. And if this list all equals to C0, then I have C2 alpha estimate, right? Actually, I better define in general this way, but I need this condition also. Okay, so I have a theorem with two conditions. F0 equals to 0, and the semi-norm, this kind of pointwise semi-norm, small. And okay, so F0 equals to 0 is not a condition. For Laplacian equation, it is not a condition. But if I do this for minimum surface, I do it for harmonic map, this becomes a condition. This is usually is an unavoidable condition. But for Laplacian, this is not a condition at all. So for example, Laplacian U equals F, right? I can make F0 equals to 0 just by minus half F0 x1 squared equals to fx minus f0. So this, my new f at origin will be 0. Now this small is not a condition either. So how can I make this thing small? I just say, I first normalize it, right? By my notation. Then this will be 1. Then I multiply epsilon 0. I cheat, right? Then the small constant multiplies the function is C2 alpha. Then the function will be C2 alpha. Then you might argue that this thing is not bounded by 1. Then you can cheat further. You can say use every infinite norm, right? Then you prove the ratio multiplied by small constant is C2 alpha. Then it's translated back to the original U is C2 alpha. And it's really is a two important steps. One is normalization, scaling, and you do it infinite many steps. And philosophically is that you really, from this average infinity to average infinity estimate, you get Holder to C2 alpha estimate. You have the quantum leap. You gain two derivatives through infinite many iterations. Okay, so now, if you like this picture repeats to any other norm you like for linear equation. Another comment I want to make is that this step for linear equation you can just do like this. For minimal surface for harmonic map, you cannot do this. So in that case, you have partial regularity. You do exactly the same. You get partial regularity. The smallness is not automatic, but for linear equation is automatic. So L2 approach. I have 7 minutes and give you another proof. So a lemma. Clear, right? We did it. Then what that means is really an error estimate. It's F's L2 norm is controls gradient use L2 norm. Then key iteration is this. For alpha bigger than 0, less than 0, bigger than 0, less than 1, there exists epsilon 0 R 0, exactly the same. F, the normalized, this is for 1. If this is true, I better do this. But the scaling has to be friendly with respect to scaling. And I assume that. I square it because I want to scale like that. Then you say second order harmonic polynomial. Exactly P as before, such that gradient P minus U minus P. And square. And I better times R 0. So this whole thing has a scale of U. Okay, I average has no saying of the dimension in R. This gradient cancels with that. And the proof exactly the same. You separate U into low frequency part, high frequency part. High frequency part is almost like a 0. So U minus a polynomial will be as small as you want, actually. But you put it in this fashion. Then the iterative step, and you have the same picture, but this direction is not the naked eye can see. What you see this direction is H. People use this homogeneous part of L2 norm. And this also is H01. Exactly same picture. Then what do we have at the end of the day? At the end of the day, by the way, this P, the constant term won't under control because this don't give you under control of the constant. That's the only difference. But all the second order derivative, first order derivative is under control. Then at the end of the day, you get this estimate, U minus P infinity squared. Well, for all R, because R, you shake it between two geometrical radiuses, less or equals to C1 R2 plus alpha. So what does it mean? This says that U is C2 alpha at D0 in H10 fashion. What we did before is, you can see by naked eye, is U is a C2 alpha by this L infinity, physically exactly. But this is by this kind of semi-norm. Then in the 60s, the Italian mathematicians, Capinato and their colleagues proved that if this kind of estimates, of course, this doesn't mean U is a C2 alpha at all at the origin. All the geometrical imagination which is suited by this inequality, that's correct. It can be wild because it's only measured by this energy. But guess what? The Capinato says that if this inequality is true for all the zeros with all the zero, then it's classically C2 alpha. They're all equivalent. And that's the theorem of Capinato. Let me state one of the theorems to warm you up. Is F minus F's averages in ball R squared, ball R square root divided by R to the alpha. You take soup, You take x in ball 1. This basically says f by reasonable approximation of a constant, which of course the averages. The error, the L2 norm, is decays to R to the alpha. This is controls f's C alpha norm all the way up to this boundary. And the only thing is they are not equivalent because when x near the boundary, the ball R of x go out. That's the only place. It's like annoying. And you can make it necessary, and this is perfect if you restrict yourself. Then they are equivalent. So what this says is that in L2 fashion, if you say f is Holder continuous at every point, every scale, is for all x, all scales, then the L2 fashion Holder continuous and L infinity fashion Holder continuous. This I defined before. This is naked eye Holder continuous. They are all equivalent. And of course, for this gradient, because L2 is true, then any other norm would be true. And say you can put a P here, you can put sublevel spaces. Of course, everything should be reasonable. It's like if here you have a gradient, you have a holder. If you have gradient, you have R here. Then not all the Holder continuous has a weak derivatives. So you have one-sided inequality. Other than that, morally, you measure the Holder norm for any norm, every point, every scale. They're all equivalent to the classical one. And in terms of Schauder estimates, is what we just did is in terms of Laplacian, if the equation is a C2 alpha, then the function is really C2 alpha. And that's the Schauder theory. So next time I'll prove DeGiorgi. Okay, thank you.